All right, I'm gonna start on station 2 here. It says, how do you find the velocity of a balloon racer? Right, so the balloon racer we could draw right here looks something like this. You got a little straw that comes out the back, little balloon on top, pushing it forward, and some wheels, right? So how do you find the velocity of this thing? Well, you have meter 6 and a stopwatch. You can find out how far it goes, take the distance, right? And then divide by how long it takes. So, and divide by the time. Easy, right? That's our basic velocity equals distance over time equation. Just the main thing is make sure you get the order right. You have to divide by distance first, then time. It doesn't matter if it's a bigger number, smaller number. Distance goes on top, and then time, okay? So the free body diagram, this is the one where you have the different forces that are acting. So, right, so it's on a little table. So obviously, force that's acting on everything, gravity, right, is pulling it down towards the earth, force of gravity. But it's not sinking through the table, so there has to be another force balancing out the gravity, right? That's the one going straight up against gravity. We call that force normal, okay? And again, if you need to, pause the video if I'm going too fast, and make sure you get all of these down because you need to know all of them. The other force, well, the balloon's pushing it forward. Usually when we get a direct pushing force, we call that force applied. Okay, so the force is applied going forward. But it's not going forward perfectly. There's a little bit of force here, just a little bit, pushing back. And that's the friction between the wheels and the table. So force of friction. Okay? And then, of course, if it was in the air, you would also have air resistance. So if on the test, the free body diagram is like an object in the air, like a rocket ship or, a free-falling parachute person, don't forget about air resistance, okay? This question here, if you added 2 extra balloons, which would triple the amount of force, what would happen to the acceleration of the racer? Well, force and acceleration we know are directly proportional, so acceleration would also triple in this case, right? So I want you to be specific. Don't just say it would increase. Tell me exactly how much. It should also triple in acceleration, right? All right. So the next one, the F equals ma equation is very important, right? So let's look at these here. So the first one, what is the force on a 1,000 kilogram elevator that is falling freely at 9.8 meters per second? Well, it's looking for the force, right? What is the force? And it gives you mass and it gives you acceleration. So that's an easy one. You just do 1,000 times 9.8, right? Mass times acceleration. So of course it'd be 9,800. If you got that wrong, make sure you go back and see what you did and how to fix it, okay? Next, we have number 2. What is the acceleration of a 50 kilogram object pushed with a force of 500 newtons? Okay, so now we have a force and we have a mass and we don't know the acceleration. So we've got to use this equation, right? So we know the force is 500, so we write that down. And we know that force equals mass times acceleration. We know the mass, so we'll write 50, but we don't know acceleration, so we can just put an A in there, okay? Right, so just like in your math class, you have to do an inverse operation. You want to get the A by itself. You want to get acceleration by itself to find out how much this car is accelerating. So we have to get rid of the number next to it. So you're dividing by 50 in this case, okay? So this cancels, of course. So now we have A equals 500 divided by 50, which would be 10. So equals 10 meters per second squared. Make sure you know meters per second squared is acceleration. Force up here is newtons. And then we'll do a mass problem right now, which is going to be in kilograms. So problem 3, a force of 250 newtons is applied to an object that accelerates at a rate of 5 meters per second. What is the mass of the object? So we need this equation again, right? And we know we need this equation because it's talking about force, mass, and acceleration. If it doesn't have at least 2 of those things, it's not the right equation. You're not doing the right thing, right? Like if it asks for net force and it only gives you 2 forces, you're not doing this equation. You're doing either subtraction or addition. All right, so for this one, a force of 250 newtons, so it's 250, right? That's force, equals, we don't have mass, so we gotta just write m, okay? And it's accelerating at 5 meters per second squared. So we can just write a 5 right there. So again, we just gotta get rid of this 5. That's it, cancel it out. 5, so that'd be 50. So mass equals 50 kilograms, okay? Very important, you need to know these. All right, next was station 4, vocab. All right, so the vocab you needed was net force, right? This is all forces on an object. Okay. For these ones, if you're struggling, go on Quizlet or make some flashcards and study them. Just set it up, right? Net force on one side, all forces on object the other, and quiz yourself. That's the best way to learn these vocab words. Vector is magnitude and direction. Remember, magnitude is how much of something, and direction is where it's going. So what are our vectors? One of our vectors was velocity, right? This has magnitude and direction. The magnitude is the speed, and then what way it's going, direction. Another magnitude we had was displacement. Or sorry, another vector that we had was displacement. This is the direction you're going. That's your magnitude, right? Like 100 meters, 100 yards, something like that. And then, of course, the direction. Then we had velocity. Oh, force. Forces are just pushes or pulls, right? They cause objects to move or change direction, push or pull. And then lastly, we had acceleration. So acceleration is getting faster. It's a change in speed or direction. So it's actually a change in velocity. So acceleration is a change in speed or direction. So you need to know those vocabs. The acceleration lab, you got something that looks like this. Okay. So on this station, right, they're asking, someone set this up to see how the acceleration of the car changed with changing mass. So the mass is here on the car. That was a little tricky. Sorry about that. Mass is here, and then this is the force on the car. So in this lab, they're dropping different forces that's pulling the car, and we want to know how the acceleration changes if we change a few things. If we change the mass, if we increase the mass, right? Mass, acceleration. If we increase the mass, what happens to the car's acceleration? If this car gets bigger, what happens to the acceleration? It goes down, right? If you double the mass, the acceleration cuts in half. What if you double the force, though? Like force, right? What happens to acceleration? So now we have more force on the car. Does it accelerate more or less? Does it get faster or does it, not get as fast? If you increase the force, you increase the acceleration. And it's directly proportional. If you double the force, it doubles the acceleration. If you triple the force, it triples the acceleration. If you cut the force in half, the acceleration goes down by half. Okay? So that's what you need to know. And that's what we learned in our notes on those pages. But then when we did our lab, why might their data be flawed or inaccurate? We didn't get when we doubled our force, the acceleration doubled. It wasn't a very clean. There was inaccuracies. There was error, right? Error, E-R-R-O. What was the cause of all that error? Well, what's going on right there? Between the wheels and the table, you got friction. That's a big one, right? So friction is a force. We learned about that from our free body diagrams. So when we changed the force on the car, it wasn't taking into account that the friction force was going against it. So we didn't really double the force. We doubled the force we hit it with, but then friction went up as well. And since we didn't account for that, our data wasn't as good. There's also other issues, right? Human error, like maybe the equipment is faulty. Equipment, let's say uncalibrated, right? Or faulty, or the equipment's out of date, right? Maybe this pulley doesn't work very well. Maybe these forces are off. And then also just human error in general, right? But definitely talk about friction for a lab setup that looks like this. right? This is similar to what we did with our force pushing thing where we changed the mass, added mass to our iPad, and so on. Okay? And then lastly, station 6. You need to know these two different graphs. So this is a distance versus time graph. On this one, this person going up, the slope of the distance versus time graph, remember, slope is rise over run. So if you look at a graph like this, the rise is the y-axis. That's distance. So the slope is the distance over the run. That's the horizontal time. What is distance over time? Well, hopefully we know by now that's our velocity or speed. So the slope of this is telling us our speed, right? So when he's walking these 15 meters in 5 seconds, right? 15 divided by 5, he's going 3 meters per second. So we tell the velocity by the slope. So then he's walking here. He's going a constant velocity because it's a straight line. But then he's doing something different here. He has a different slope, which means he's going at different speed. And you have to know who's going faster, A or B. So from our notes, you hopefully will say A because the slope is higher. So this higher slope means higher speed. Okay, C, right, this part here. So his distance is at 20 here at 15 seconds. And then 5 seconds later, at 20 seconds, he's still at 20 meters. So he hasn't moved at all. He hasn't gone anywhere, right? This is measuring the distance. If his distance isn't changing, he's just staying in the same spot. So not moving. And then here he goes back to wherever he started from, right? So his distance decreases. He's going back to where he started from at the beginning. So this one here is a speed versus time graph, or a velocity versus time graph. So this is a little different. Now what is the rise over run? Now we have speed or velocity over time. That's acceleration. So the slope on this graph tells us acceleration. So at A right here, he's going up in speed. So if he's gaining speed, that's what we call acceleration. That's it. So he's getting faster here. This would be like, if you're in a car, this would be like hitting the gas pedal, okay? Here, what's going on? Some people get confused and they say that there's no movement here. Well, yeah, that's true over here on our distance time graph, but now this graph is showing speed. So this right here, his speed is not changing, but he does have speed. He's going 15 meters per second. That's, that's pretty fast. He's riding a bike probably. Every second he's traveling 15 meters, maybe a car going kind of slow. So right here, he is moving just at a constant speed. No acceleration, but there is movement. So you need to know that. This would be like cruise control on a car, right? You just click the button and you just keep going the same speed until you hit the gas or your brakes. Of course, he goes faster again. And then here, he's getting slower, right? This is like hitting the brakes in the car all the way back down here. This right here would be no movement. This over here would be no movement because the speed is 0. But up here, definitely movement. Don't get confused on that. You've got to pay attention on the test. Are you looking at a distance time graph or a speed time graph? Okay? And that's pretty much it. If you can do all of those things, and then real quick, don't forget about net force. So like if you're pulling on an object, right? Net force, let's say 5 newtons, 6 newtons. So right, you have 2 people pulling on it, net force. Well, they're opposite directions, right? So when we combine them, we have to subtract. So this would be, and then force is not negative, so you do 6 minus 5. So 1 Newton on this case. And then also know that if they're going in the same direction, right, they're helping each other out. Let's do 5 and 6 again. This time, because both forces are going in the same direction, we add them. So it'd be 11 Newtons, okay? If you can do all of this, you should be good for your test. So make sure you study this, make flashcards if you need to make flashcards, quiz yourself, whatever you need to do. And as always, don't forget to hit like and subscribe. Thank you.